Welcome, ladies and gentlemen, to the afternoon session on automated vehicles and collision avoidance. My name is Chris Stiller from Karlsruhe Institute of Technology, and we have four speakers who will present papers on this topic, shedding light from very different aspects on automated vehicles and collision avoidance. And the first speaker will be Ashley Napier, who works with Paul Newman in Oxford University in the mobile robotics group. Please.
Okay, thank you. So I'm Ashley Napier. I'd like to talk about some work that I've done with Professor Paul Newman on the generation and exploitation of local orthographic imagery for road vehicle localization. So first, just a few words on our group. We're very interested in autonomous road vehicles, and the way we approach the problem is to have these vehicles operate on the existing infrastructure in the road network. We don't want any modification. We don't want any beacons or anything like that. We think there's enough information there to enable autonomous vehicles to drive themselves. We do all this based on local sensors, mainly cameras and lasers, in order to avoid any reliance on GPS for the reasons which have been made explicit in a lot of the talks so far. So the part of the problem that I'm particularly interested in is answering the question, where am I? This is particularly important for autonomous vehicles because if you're wanting to control the position of a vehicle and its velocity, you need to be able to accurately measure these two things. So we want accurate and reliable vehicle localization pose estimation, and we want it to be persistent. So we need to know where it is all the time. So my approach to this problem was to use the onboard cameras, specifically a stereo pair which is mounted on the front of the vehicle. And there's two distinct stages. The first stage is a survey where we go around and generate this high-fidelity map of the workspace, which is in the form of local orthographic images of the road surface. And the second stage is localizing against these images. So why use the road surface? Well, our application domain is road vehicles, so we're generally on the road. And in normal circumstances, there's a few meters ahead of the car where we can see the road surface. It contains lots of nice features such as road markings, the sort of texture from the actual tarmac itself, and there's drains and things like that. There's lots going on. And it's very non-ephemeral, so it's long-lasting. We can do a survey, and that survey is going to be good for quite some time. And the other thing is that it can be approximated as planar over small regions, so it lends itself perfectly to the generation of these long image strips of the road surface. And we want to try and use its gross appearance. So why do we want to try and use its gross appearance? Why not use one of the many feature-based approaches that are out there? Well, what you can see there in the top of the two images there is a stereo pair and SIFT features matched between the image. So these is a very minimal representation of the world. So all the system can see is a set of 9x9 patches. And these are great for VO and frame-to-frame matching, but in terms of going around a route and then driving it again at a different time, their usefulness is limited. So for example, you see there's lots of features on greenery there, there's features on a parked car. These, and on the road as well itself, these little tiny patches of speckle on the tarmac, the chances of you seeing those again when you traverse the route again are pretty minimal. So we tried to demonstrate this by driving around a route once, making a map of these features, then driving around again and localizing the vehicle relative to these features. And what we saw was that about 40% of the features are visible the second time round, and then driving at different positions on the road and various other conditions, after about 80 meters, the system fell over and we were unable to localize. We tried again 3 more times, but the furthest we got was 200 meters, and we think we can do better than that using the gross appearance of the road surface. So, how do we do it? The first stage is a survey. We leverage state-of-the-art stereo visual odometry, and we use that to generate these synthetic overheads over there. So more details on that. From the VO system, we get given a list of poses for all of the image taken and corresponding 3D locations of all the landmarks we've observed. So from this, we can generate this sparse point cloud, and that allows us to find a ground plane. We do this with Ransack, and we make life easy for ourselves by having the camera pointing towards the ground. So a lot of the features we observed are coming from the road. Then, for each of the images in the set we've taken, we compute the homography between the image itself, or the image, part of the image corresponding to the road, and compute the homography between that and the local ground plane. And we do this for all the images, and the VO operates at about 20 hertz, so there's a lot of overlap in these images, so that allows us to do a little bit of blending, and in our case, we just average out the intensities in the local orthographic image. So now we have this orthographic image that we know its 3D position in space. So from a survey trajectory, we can move out a virtual camera and generate a synthetic view of what the road should look like from a different position. So the composite image here allows us to have very big changes in viewpoint rather than being restricted to small changes which would be possible with individual frames. So cameras can be mounted at different positions on different vehicles, it doesn't matter. So we want to be able to use these synthetic views to tell us something about where we are. So this next step is then localizing relative to this survey. So what we have coming in is a stream of images, and what we need is to start us off is some rough relative motion estimate between these images. In our case, we use the stereo VO, but these relative poses could easily come from an IMU or even wheel ticks in the simplest case. So this first guess of relative motion can then be used to pick out the closest pose in the survey, and then the most important variable in all this work is this next thing, ITK, which is the current vehicle pose relative to some pose in the survey trajectory. So we're now in a position where, with a live image, you can see in the bottom there, and some rough estimate on our motion, we can then say where we are relative to a survey trajectory. And if we're right, the image we synthesize from the orthographic imagery should match up with the current view. If we're wrong, it won't. So the problem then becomes maximizing the alignment between the live view and the synthetic view via this pose relative to some survey trajectory. So the correlation measure we use is mutual information. There's been a lot of work done with mutual information lately, and it's been shown to be a very good correlation measure and has robustness to variations in intensity, lighting intensity. It sort of copes quite well with partial occlusion, and it's sort of intuitively bounded. So it's defined as the sum of the individual entropies of the two images you're comparing, take away the joint entropy. So you can write this out a little bit more clearly in terms of the distribution of pixel intensities. So this is effectively the probability of a particular pixel in the image having intensity n. You can do that for each of the images individually. And then you compute the joint as well, which is the co-occurrence of intensities. Put those back together and we get mutual information in its explicit form. And I sort of like to think about it as a measure on how independent the distribution of intensities are in the image. So say, for example, if you have two images which are well aligned and they're of the road. If you see white pixel in one image from a road marking, say, in that same pixel location in the other image, you can then infer that you're going to see a white pixel because these images are aligned. If they weren't aligned, an intensity value in one image would not tell you anything about the other image, and you'd have no mutual information. Okay, so we're now in a position where, given a pose relative to a survey trajectory, we can generate this synthetic image of what the road should look like. We have a nice robust correlation measure, which we can use to measure the alignment of these two images, the live view and the synthetic view. So then the problem reduces to maximizing this correlation measure based on the pose relative to the survey trajectory. So we do this first by making an SE2 approximation. So rather than having a full 6 degree of freedom problem, we reduce it to 3 degrees of freedom. We do this because the gross motion for road vehicles is in plane, so we can make that assumption. And it also allows us to use a histogram filter, which is effectively a grid search. And from the initial seed, we can explore the feasible workspace and avoid any local minima or anything like that, because we're forcing the optimization to look at all the feasible possibilities. Another good thing about the histogram filter is a very easy parallelizable, so you can throw a few cores at this and make it as fast as you like, and it's very easy to change the way you're searching the workspace, and there's no need to compute the Jacobian. Okay, so these are some results. The live image stream there on the left, and the matched synthetic view on the right. And you see this system copes rather well. Those two views are quite aligned. The camera's moving around. We've got some occlusion on the other side of the road. And the system seems to cope quite well with that. So we've successfully tested the system on 1.4 kilometers of test track. The pose estimation was persistent. We didn't have any interventions required. We didn't lose track of the vehicle pose. The actual matching process between the live images and the synthetic images was available 70% of the time. When it isn't available, we fall back to the raw VO, which is good enough to go for a couple of meters before the matching is re-established. And we found that matching wasn't available in these indicated regions here, where there's no distinctive detail in the road surface. It's basically just tarmac. And with the SE2, we found that with the SE2 approximation, we couldn't leverage this very fine detail because the small errors in pitch and roll just meant that the mutual information just couldn't see it. So I'll talk about that more in a second. In terms of demonstrating accuracy, we don't have centimeter level ground truth, so the way we try and show accuracy is by taking in the top an image which we know is well aligned, and then showing the difference between the live image and the synthetic image, and you can see that it's all black there, so the pixels agree with each other. In these other images, we perturb the pose artificially, moving the vehicle 10 centimeters forward, 5 centimeters to the left, sorry, and we rotate by 3 degrees. And even for those small images there, it's quite clear by the human eye that there's a significant misalignment between those images when the pose is in error of the order of a few centimeters. So when we compare this to a live run, you see those are the live images, those are the synthetic views, and those are the differences. And you can see, I think we're justified here in saying that the vehicle is localized within the survey to the order of a few centimeters. And this is over the course of a 700-meter trajectory. So getting back to the problem with the SE2 estimation and the not being able to leverage fine detail, we're currently working on a full SE3 solution. So this allows correction of very small errors in pitch and roll, and this actually does allow us to match on just raw tarmac itself. So there's enough texture in the tarmac to actually to get a good match. Currently, this is not real time, as the histogram filter doesn't really scale well to 6 degrees of freedom. So we're going to have a different approach for the full SE3 solution. So finally, a word on the robustness of this mutual information correlation measure. On the top here, you can see normal operation and the live view and the synthetic view, or the hypothesized view. And there is the first plot there is translation, so that shows you how the mutual information changes when you translate the vehicle pose around the true position. And the next plot is for rotation. You can see there's a nice distinct peak there. The scale along the bottom, it's not quite clear there, but it's half a meter. And again, for B, with no road markings, and we're just looking at the texture in the actual road in all 6 degrees of freedom, there's a nice distinct peak in mutual information. We have C, where we have partial occlusion with a vehicle on the other side of the road. And also in this case, we're driving quite far to the left of the original survey trajectory, about a meter or so. And we still have a nice distinct peak and a relatively smooth cost surface around the true position. And finally, we've done some tests with wet and glare, and we are still maintaining this nice peak. And yeah, that's everything from me. Thank you for listening, and hope you enjoyed it.
Yeah, thank you. The floor is open for questions. I already see one with Uwe Franke.
Well, nice work. It seemed that all the videos were taken when the sky was covered by clouds. So if you go out by sunny day like today, but you do this in the evening, when you have low sun, you will see your own shadow, you will see the shadows of other moving objects. Will that, will your algorithm be able to work with that, or will that lead to wrong results?
We haven't done extensive testing in these sort of situations, but on the bottom plot there, D, you can see there's a significant amount of glare on the road there, and glare and shadow would effectively be seen as the same thing to this correlation measure. It's just a difference in intensities. But we're still able to have a distinct peak in the cost function. So I'm quite confident that we'd deal with shadows and things like that.
A question, maybe in the front here?
At the start of your run, you need to provide extra information to the system about the starting point.
Yeah, so we...
Just repeat the question.
Sorry?
Could you just repeat the question, because you had no micro?
Okay, so the question was, do we have to provide any extra information when we actually start the vehicle, so an initial pose? And in the current system, this system alone cannot localize if it's lost in a map. So we do actually have to tell it where it is initially, and then it can track its position. So we have other systems within the vehicle that can find the vehicle's position from lost. This isn't for that purpose. Okay, thanks.
Okay. There's time for one more question. Mr. Leitegan.
You're pointing your camera towards the ground.
Yes.
I can well understand why you do that, but I'm wondering if you're experiencing any problems with motion blur. Or to put differently, what velocity can you not exceed before you get into problems with motion blur? Or did you not experience that?
Okay, so basically, the camera isn't pointed directly at the ground. We've specifically mounted it so it's orientated about 15 degrees. So the field of view contains a lot of the road, but a lot of the road is very far in the distance. You can see there with these road markings up there are sort of about 5 or 6 meters away from the vehicle. So in terms of motion blur, if it was very dark and the shutter speed was high, we'd definitely see some motion blur, and it would be a problem to the system. But at the speeds that we were going here, which was around sort of 20 miles per hour, we didn't see any motion blur. But I imagine it will be a problem. But I think that's a problem that will be solved by better cameras rather than clever software.
Oh, thank you.
Okay, thank you very much. We have to defer further questions to the break. Let's thank the author again. And we will proceed to the second presentation. While it's set up, we move from localization to planning. Planning autonomous vehicles in the absence of speed lanes using lateral potentials. And the paper is presented by Carla Raoul and co-authored by Kevin Warwick.
Thank you. Well, I've got a very unusual kind of problem statement. So straight away, let me put forth a question in front of the House. Now, you all represent different aspects of the intelligent vehicles or the transportation system. What if I take your module, implement in a vehicle or a transportation system, and have this vehicle or system implanted on the Indian roads? Do the algorithms need to change? Do the same algorithms work? Well, yesterday we had an interesting presentation in the last session, Professor Anderson explaining his work, and it did seem that those algorithms work on the Indian scenario who was doing for the semi-autonomous vehicle. In fact, MIT's algorithm, I believe, do work because even the DARPA entry challenge was somewhere which does not rely on speed lane. And that is what differentiates the Indian traffic with most of the European or the American traffic. In India, there are speed lanes, but they are never followed. So virtually there are no speed lanes. It's an unorganized traffic. It's a chaotic traffic. Now, what do we do if we need to plan vehicles in such a scenario? And that is what I'll be trying to do. So again, coming up onto the major question, what do we do if we have such a kind of scenario? Normally, from a diverse crowd, I expect three types of answers. A, they would all work. B, the Indian traffic needs to change. There's no use of such traffic. And C, that in Europe and America or the other parts of the country, even Spain, such things are not at all possible. So for those of you who had A, that they would work, unfortunately, in literature, we do not see such kind of simulations of algorithms, even though people may claim that lane is not a major factor. For B, you go to any Indian road, you'll see that the traffic bandwidth is much more than what is actually possible. So there's, by not having lanes, we've increased our traffic bandwidth. And if your answer was C, then you need to understand why is it that not having lanes, it improves the traffic bandwidth. We are a very diverse traffic over there. We are such a diverse traffic that the width of vehicle will vary from the two-wheeler bicycle to the motorbikes to the three-wheeler auto rickshaws to small cars to big cars to trucks, buses, and the heavily loaded buses. In terms of speeds, we would vary from the slow-moving cycles to the fast-moving motorbikes to the still faster-moving cars, very slow-moving trucks. So it's a very dynamic kind of landscape. In fact, if you are there in the rural roads, you might find bullock carts and all these, which constitute traffic. So if such kind of, autonomous vehicles come in, which give you that diversity, would you prefer having lanes and a low bandwidth, or not having lanes and having a high bandwidth? Already I've been told that in some US cities, it is possible for motorists to drive in between two vehicles. That's known as lane splitting. So that's what is my major module that I need to plant inside this house. That's what's the main agenda of my work. And I say it main agenda because normally after this, nobody listens to me. So I'll discuss in how do we do the planning in these vehicles. And people do not listen to me because they say there are so many problems. You would expect a person to normally come up with a vehicle, have all the modules made. We tried doing that. Of course, there were limitations that it was completely out of the project scope. So right now I'm here, which is what my PhD is based upon, only one module of this entire bundle of problems. And I normally do not look outside that. Once I'm happy with this problem, then let's see how do we tackle the other problems. So if we do some kind of trajectory planning in such a diverse spectrum, what do we do? Well, my personal comment on to what's happening in the European and the American lane-prone traffic, you either follow vehicle or lane change. That's effectively what you do. And that's a very kind of boring traffic that you have. I do much interesting stuffs. I mean, sometimes I act like a small 4-year-old kid who's playing with cars. So I can have cars with a close cut-in, I can have cars squeezing in, I can have all these types of exciting things that you may imagine. In fact, out sitting here, even if you imagine what can be the traffic landscape, if you do not have to drive within the lane, it's immense. There are immense behaviors, there are immense possibilities, and how do we do all this? That's what effectively my work is out there. Now, we tried in many methods. Anybody here would be knowing that in research, first you try to have simple systems, then you complicate the systems, you make hybrid systems, you do simple planning, you do hierarchy planning. We effectively did all that. But what I am presenting here is what I did after all these works, and that was nothing but a very silly thing to reduce to the simplest possible algorithm that literature would produce, and that is called as the artificial potential methods. By the way, we do not take our algorithm from the transportation domain exactly. We try to take our algorithms more from the mobile robotic domain. And in the mobile robotic domain, it is certainly the most simplest algorithm. So why do we do that after having all such things? First, of course, we ourselves realize that it takes a lot of effort to us to make in complicated systems, to which there is probably few or no literature that other people are doing. So it's good to present an algorithm that others can replicate and then build upon. And secondly, we of course thought that we are making in complex architecture, complex by architecture, not by the computation time, that we ourselves find it very difficult to extend. And the result that we obtained, what I'm be presenting here, that simple kind of systems can really generate in this madness that I wanted to create. I mean, having different vehicles in the entire landscape, doing things that many people may have seen in Indian scenarios, but more importantly, because traffic dynamics of a particular country may not represent the entire dynamics possible. So we can do really crazy things out there, and by a very simple algorithm that I'll be presenting. A brief primer, not everybody may be from the same domain. So potential field is nothing but the goal. It attracts the robot towards itself, and the obstacle repel. So if my robot starts over here and it by chance goes near, the obstacle will reflect and it will be ooh, and it will fly away, and then it will again be attracted by goal. It will always be repelled by the obstacle, and then ultimately it will reach the goal. It's that simple an algorithm. When applied to the problem of planning, now mobile robotics has no lateral and longitudinal, which is a very important concept. So we take this from the transportation domain, that planning is lateral planning, which is more of a steering control, and longitudinal planning, which is the speed control and keeping within lane if you are having a lane typical scenario. We don't care about the longitudinal planning, although there have been many papers presented at this conference itself. We are much more on to how do you steer the vehicle all around. So that's the coordinate system of use. It's completely dependent on road. There's a lateral axis and there's a longitudinal axis, and that's all what this represents. But that's not that simple. Of course, there's a little bit of glitch that we cannot use artificial potential field algorithm over this problem. Now, why do I say we cannot use artificial potential field method? Because in mobile robotics, this method says there are a few scenarios where you cannot implement it. In scenarios where your robot is big and it's a narrow tunnel kind of system, which road system is, your vehicle will start oscillating if you use this method. In driving, I love such kind of driving, but unfortunately, we cannot sell cars that make the car go roundabout on a very straight road. So we cannot directly use the system, so we've only taken a basic inspiration. Now, the arrows that you see out in this figure is what we've sampled the entire space into. We'll be only seeing the obstacles ahead, at the two diagonals, behind. Now remember, when I say ahead and when I say behind, it does not mean what others say ahead and others say behind. Those people have got the lane fundamental, which I do not have. Now, if there are people in mobile robotics, what you see out in this figure, the front vehicle will repel the vehicle at back and the behind vehicle will repel the vehicle ahead. And the two forces cancel each other out. So the vehicle effectively does not move, and if I apply a goal that it's attracted towards the road, it goes ahead, problem solved. But what vehicles people would see, that if this vehicle at the center is a very high-profile car and it's like a very expensive, fast-moving car, so it would try to overtake this blue car ahead. If it's a very slow-moving kind of car, or let's say it's a heavy loaded truck. On the other hand, the reverse holds for the green car and the pink car. So this we need to add in our algorithm. And that is extremely simple. I mean, what the potential people say that an obstacle, two vehicles will repel each other. We say that they will not repel each other. Every vehicle will tell the other vehicle whether you need to turn left or you need to steer right. Every obstacle tells the vehicle whether you need to steer left or right. And you can, once you know whether you need to steer left or right, then the first problem is solved. The second problem is by how much you need to steer. The potential field only uses distance measures. Here we are slightly more complicated, so we use the velocity measures and distance measures, which is, of course, people working in the potential would be able to understand why and all. I won't go into the details, and I'll probably wind off the presentation with some extremely good things we've done. The normal people will find that a very risky kind of driving, but then we've done obstacle avoidance. We've done overtaking when there was an obstacle in behind, two vehicles following each other. Many people ask this question, what if many vehicles are there? They simply follow each other. That's a very boring kind of this thing from up. That's a very boring kind of traffic dynamics. We can, of course, generate that. One vehicle squeezing in between, so lots of interesting things we do. And of course, there are parameters, and they have some trade-off which they play in various kinds of scenarios. I never leave any opportunity to not advertise myself. So this is what would be soon published. It's available on pre-order. It's a book on robotics, not intelligent vehicles. And my last conclusion would not be on what I presented. My only point of conclusion would be, think about whatever problem you are solving, and might not be as research, but maybe as puzzle, maybe as a tweak question to keep you awake. Think about whether that problem is applicable in an unorganized traffic, in a chaotic traffic, in a highly dynamic traffic, and we can take in questions.
Well, thank you very much for this presentation, and I would be quite sure that there will be some questions to this.
Meanwhile, there's some entertainment in background.
Maybe I'll start with the first question then. Did you ever think of a proof of integrity of that, of your lateral guidance? Like
proof as in completeness.
Like those potentials, I would expect if somebody swerves towards you, you would evade. So you might send the wrong signal in chaotic traffic that you give him way. which you actually might not want to do because the gap might not be enough for you. So it might be another strategy to stay consistent and signal somebody who goes towards you that you will not give any pass.
I guess you are not considering that if there is no way, the road boundaries and the other vehicle have got immensely high potential for the vehicle to move on the other way. So basically what will happen is the potential, it scales to inverse of square of the distance. So even if it moves a millimeter here, it will immediately be this thing.
Okay, my question was related to mixed traffic, where some humans drive as well.
It is on mixed traffic.
And then, of course, other vehicles might be driven by a very different strategy.
So the algorithm
see that potential to evade.
The approach we have entirely based on this system that while planning a vehicle, others are being planned by completely independent vehicles. If I understood your question correctly, you had two vehicles at side, one vehicle at center, and a vehicle behind. Or let's say a vehicle at side, a vehicle at one side, a vehicle at center, and a vehicle behind. So there are 1, 2, and 3 vehicles. You say that this vehicle will ask this vehicle to move here so that it can overtake.
No, if it just does. If you have 2 vehicles driving just aside, and one vehicle swerves towards you, then your potential field will make that you evade this vehicle.
Yeah, so and there's no enough distance.
Might believe that you actually evaded, so you give him more space, which you might not want to do because you might then drive in a more narrow path than you wish to do. So you might want to give the opposite sign. When he moves towards you, you say you also move towards him to say, I stay here.
Okay. Let me only talk about the perspective of this vehicle in between.
Okay.
There is a vehicle here and there's a road boundary here. No space means there's a road boundary. This applies a force to this vehicle. Let me say this asks the vehicle by a weight of 0.8 to move this side.
Okay.
Because the distance is small, it will ask by weight of 0.8 to move this side. This road boundary will also apply a force on this.
Okay.
Road boundary also applies a force.
Yeah.
So the road boundary will also apply a force of say 0.7 to move this side. Now when I say that this is 0.7 and this is 0.8, that means the vehicle is closer a little towards this thing.
Okay.
So when it moves such that both the distances are equal, then it will become, let's say, 0.75 and 0.75. Now the two forces cancel each other out.
Okay. Thank you. Any more questions in the audience? I do not see that, and oh, sorry.
So in the past, I've explored ideas like this, and one of the things that comes up is smoothness of behavior. So, you know, if you look at Indian traffic, it's incredibly chaotic, but I'm always struck by how fluidly they move through it, through the intersections and whatnot. Looking at your animations here, it's very abrupt and kind of jerky, and that's because, you know, you have a limited depth look ahead. How do you make the behaviors more smooth?
That's an interesting question. It normally comes from people who are doing reactive planning, because reactive planning, it makes you oscillate, which is what your question is related to. I've skipped out these slides. The parameters control it. I mean, basically, be it any reactive methods, if you try to make a system over it, by addition of some kind of parameters or by studying what forces can you modify. So we've done that. But that's too specific to the algorithm. There are parameters which control this smoothness.
Okay. Let's thank you also again. And we stay with the third presentation in the planning task, but go on high-level planning. Actually, the paper is entitled Object-Related Navigation for Mobile Robots. And we also move from United Kingdom to Germany to the University of Armed Forces in Munich. The presenter will be André Müller, and the work is co-authored by Hans-Joachim Wünsche.
Okay, thank you, Professor Stiller, for this nice introduction, and I want to thank the audience for joining this presentation. And I have to thank my predecessor because he nicely introduced some of the aspects of my work, and now I think you're already all awake, hopefully. So what is it all about? It's all about object-related navigation. Well, and in this presentation, I want to tell you what it is, what it means, and I have to say it's just, well, a motivation and a short introduction in the complete theme. Okay, well, there's just some introduction about state-of-the-art robotic navigation, how it is done now, and what leads to the motivation of our approach. Then about object-related navigation itself, which leads to prediction of future object states, just as an example. I will show some results, and then I will have a little outlook and show you what may be done with all this work we've done here. Well, that's our vehicle up here. It's a VW Touareg. I think all of you have seen it already in a former presentation. And actually, he's driving here in relation to this car, but I come to this later. So, to the introduction part, well, I think I can't be all too wrong when I say you can discern planning algorithms in basically or roughly two paradigms. It's on the one hand the reactive planning, and on the other hand the deliberative planning. While in reactive planning, well, as the name states, you react to your environment. In deliberative planning, you build a plan of the whole environment, which means you have to perceive the whole environment, you have to map it, you have to localize it, like shown yesterday in the work what Google does. You have to include all the objects, if it's static objects, dynamic objects, which in comparison all leads to long-term plans, which are then often really optimal. Well, on the other hand, you have reactive planning, which leads to short-term plans, but you can react to your environment, what you're perceiving. That means you always have an idea how to handle a certain situation. But for all two paradigms, in a way, you have to perceive the whole environment and have to, well, to make your deductions. When it comes to normal planning paradigms, you have a scenario like this one. Maybe this could be a grid where you have some obstacles here and there. It is mapped, the whole environment is mapped. And see here these obstacles. And you may deduce, okay, this may be another vehicle. And I think I'll let you guess what happens next. What do you think what happens next in this situation? Well, let me answer for you. I hope you're thinking the same. Well, basically, that this vehicle confronts us, which basically means a collision in not too far. So basically what you want to do is to plan a path like this one, right? So, but when I show you the real environment, it looks like this. It's just two bends in the roads, one to the right and one to the left. And if you just stay on your road, you can evade the obstacle. Well, basically, it isn't even an obstacle. And to do so, humans don't need to, well, observe the whole environment. They just look at the road, they just look, okay, are there some obstacles on my road? The vehicle itself does know what it's doing. Basically, in this case, it's following his own road. And as long as there is no obstacle on its road, there's no way, there's no need to replan, to rethink, or to include all the obstacles at the site. Basically, that was the motivation. Because humans are able to derive navigation solutions even in the most sophisticated areas. As we see here, it's crossroads here in Taiwan. I think in India it's not that different. You have a whole bunch of obstacles or vehicles driving around and try to drive towards the branches of the crossroad. Well, the funny thing is that humans can only perceive 5 till 9 objects. That's called Miller's Law. And so how are we able to do it? How are we able to perceive an environment and deduce plans to overcome a situation like this one? Well, it's really simply.
We just focus on the relevant information. We are not interested in the vehicles behind here. We are just maybe interested in them. We remove unnecessary information. We do not plan every new action because we know how to overtake a vehicle. We know how to follow a lane, and we know how to react in such situations. And we couple up actions to objects, which means we really perceive objects in the environment and couple our actions to them. So this is basically the motivation for our work. Our work, in a short introduction, is just we represent the environment by means of relations. Relations is just, well, another representation, not the SE2 group, which is just X, Y, and yaw. We use, well, more like a spherical representation, which has its pros and cons, but the advantages are greater than disadvantages in our work. So this is like our environment presentation. We represent every obstacle or every object in the environment by such a relation. Which means we get a set of relations, and we further define actions. Actions are simply, well, a set of relations, a set of timed relations that denote the relative motion of two objects to one another, which doesn't mean always have the motion of the robot to another object. It can also be another vehicle to the lane or another vehicle to some tree or something. And each action has a name, like overtake, follow, and so on, to make it more human-like in a way. Then again, we have plans, and plans is simply just, as the humans may think of, is a sequence of actions associated to their objects. So we can make plans like follow lane, then turn right on crossroad, follow a vehicle, and so on. As I said, we have this nice representation here, and I already said it has pros and cons. I'll leave the disadvantages out and come to the advantages. The thing is, you can really nice model your environment or actions of other objects. I have here two representations. This is our one, and this is the typical SE2 representation. And that's a simple overtaking action, which means our robot overtook another vehicle. It looks really nice. You can approximate it really good with standard approximation techniques. And here it's the same. It's a passing maneuver where our robot stood at a crossroad, another vehicle drove in front of us from left to right or right to left. Well, in X, Y, yaw, in the typical SE2 group, this maneuver looks like this one. Well, you can't really approximate it really good, and this is the passing maneuver in front. So this is one of the pros of this representation. We can model the actions between objects really good. When it comes to motion modeling, I come to the example from before. We have here our vehicle which tries towards us. And as I said before, according to its own motion, if you just use the motion of the vehicle itself, we would derive well, further states of the vehicle that drive directly towards us, which is just shown here in this little tiny equation. If you just use the measurements of the vehicle itself, you may deduce that the vehicle is driving directly towards you. If you further incorporate object knowledge, like the knowledge of the road, of the course of the road, you can deduce the further states of the object more better and even quicker. It's just shown in this tiny equation where you put in some measurements of the lane to get a vehicle state in the future, depending on the lane state and the vehicle state. But it's just normal. As a human, you already have derived an object state. Even if you don't look always the way at this object, you know, okay, there's a vehicle, it's on the other road, so it may take a certain turn or whatever. So it's really, well, natural. So when it comes to results, we tested the whole approach of predicting and navigating relative to objects, and we used it in a overtaking scenario. Well, in the next slide you see a video of the overtaking scenario, But here you have some results in, well, simple diagram. What you see here is an autonomous robot, not autonomous, an autonomous agent, which was told, okay, drive this blue line here. And the autonomous robot was told to overtake it, well, on the right side. As he did so, we increased the velocity of the autonomous agent so that the autonomous robot had to drive in parallel to this robot. And he even took this slight change of course, thought the overtaking action as such didn't account for such a behavior. And to show you these results, not just in simulation or by some graphics, I'll show you a video. Well, this object-related navigation as such, we have here a GPS track, and we just told the vehicle, I think you can see it, just follow the road, drive left on the next crossroad, then follow the road again, then drive right on the next crossroad, and it really does. It's really easy. You don't need any GPS information. You just have the relevant information you need to get to a goal point. And we just taught it this relations by just showing him, okay, that is how you follow a road. That is how you turn right on a crossroad. You see a crossroad representation. Well, the resolution isn't good enough to see it, but he always talks to you and says what he currently does. And well, you can overcome such a path, like shown here, by simple actions like follow road, take next branch right, and so on. The next video is about the overtaking. We showed him just how to overtake a vehicle. Well, that's autonomous driving. By keeping the position of the vehicle to overtake still, and we just showed him by driving around. And that's the application of the overtaking maneuver. And you see here, my colleague isn't nice to the car, and he just accelerates and let the robot overtake. It's really slow. I wanted to drive it with higher speeds, but my colleagues were too afraid to crash our robots. So what you see here above are just the relations that the robot wants to steer relative to this object. And well, when it has overtaken the other vehicle, basically the action is done. And so here, it was just told, okay, overtake the vehicle, and it did. Even thought the other vehicle didn't move according to how it should. So what is the outlook? What can we do with the idea? Well, basically, it's more an idea of object-related navigation. Well, as said, we captured human maneuvers. As I said, we captured how he should follow a lane, how he should take a crossroad branch, how he should overtake another vehicle. Well, we can do it by applying motion planning algorithms to do a sort of local planning. We can build models from captured or planned data, so we can generalize the actions. And which is really human is that we want to navigate just by actions like, okay, you follow the road, then on the third crossroad, turn right, and so on. And we want to build up maps that by the robot, or you want the robot to build up maps that include this information, which means he discovers some areas and knows, okay, when I want to go to grandmother, I have to follow the road, then take the next crossroad left, then, I don't know, steer right on some trees or on some houses with some salient features and so on. And we want to build up maps that have this minimal information, but serve well to navigate the robot along streets, along crossroads, and so on. Yeah, thank you.
Okay. Thank you for this presentation. And the floor is open for question. I already see one.
Could you elaborate a little bit on the teaching strategy? What is a database for the teaching? Do you have some statistical distribution of the tasks, or do you relate on Gestalt psychology? Or
well, currently it's really easy. And we just drove some scenarios. For example, okay, we just showed him, okay, we just captured relative data to some roads, to some crossroads, and we just made actions out of it. And we had some 3-4 sequences for one action, and he just built a mean value and some covariance so that errors are covered. So, but we will further go on further to build real models of actions. Currently, it's really simple.
More questions? And that, oh yes, there is. Yes, Mr. Görig in the center.
I have a question concerning including constraints during the execution of the task in the learned behavior, because that's usually the major challenge in such kind of approaches.
Excuse me, I haven't understood.
So you're including some constraints during the execution of the task. So if you have a learned behavior, because that's usually the major challenge. So if you do some teaching or imitation or something like this, and you have some constraints which vary from the teaching scenario, then that's the major key point you have to address in such kind of approaches.
Yeah, well, as I told, we are at the beginning of a model learning for such actions, and the scenarios we have driven are really close, not the same, but really close to the one we teach them. But well, that's as you said, major further research step.
Okay. Time for one more question. Well, that gives me time for a question, because I'm very curious. You've presented us maneuvers that were in relation to one other obstacle, which was overtaken.
Yes.
I would assume that the complexity could arrive if you have maneuvers that are dependent on 2, 3, or more other objects. And how would you plan to handle that?
Well, the thing is how important some actions are. For example, if you follow a road and then there is a vehicle what you want to overtake, clearly you have some actions that you can apply. For example, you can just say, okay, I overtake T vehicle, what is one action? Or you can say, okay, do a lane change to the other lane, follow the lane a bit, and then do lane change again. Well, actually, we can, since we have some idea of the actions, we have an idea of how vehicles move, so we can predict how an action would end up, or would end in the future. So we can basically choose the most, or the best action, or the best set of actions that lead to the goal. So you're right, when there are a lot of vehicles, it may be a bit more difficult, but if you have standard scenarios on a road, basically you have a vehicle in front, you have maybe a vehicle to the rear, and some vehicle that comes towards you on the other lane. So these are the simple tasks. And if you have, for example, crossroads, you know how other vehicles behave because you already have the models. You can apply your own models to the other vehicles, so you know what the other vehicles do and you can reason about it. So it's a kind of logic reasoning in that way.
Okay. Well, let's thank the author again. And with this, we move to the fourth presentation in this session. We'll move to Holland, to a paper entitled Improving Information Dissemination in Sparse Vehicular Networks by Adding Satellite Communication. So now we come towards cooperative forms of intelligent vehicles. The paper is authored by Hanno Speicher, Bernhard Klöber, Thomas Strang, and Gent Hayenk.
Hello everybody, welcome to my presentation about improving information dissemination in sparse vehicular ad hoc networks by adding satellite communication. My name is Bernhard Klöber, I'm from the German Aerospace Center, DLR, and I'm going to present you now the work which has been done by a former student in cooperation with the University of Twente. I would like to start with a very short introduction into car-to-car communication, which is expected to improve road safety, traffic efficiency, and, of course, infotainment services. But what we are focusing here is mainly road safety aspects. The used car-to-car communication technology in Europe is called ITSG5. It's based on IEEE 802.11p, and it's operating in the dedicated frequency band located around the 5.9 gigahertz frequency range. The communication range is, yeah, you can argue about that, up to 1,000 meters, sometimes more, sometimes less. It heavily depends on the radio propagation conditions. Here, I would like to introduce to you the problem of our work, which is that most of the research studies consider the car-to-car performance problems in highly dense traffic scenarios, for example, crowded freeways, and there a high traffic can lead to the congestion of the communication medium. That's of course problematic. But what we are doing here in our work is to focus on the car-to-car performance problems in low density traffic scenarios, for example, rural areas, or very important and interesting, initial phase of market introduction. The problem we have there in these low traffic density scenarios is that this can lead to the clustering or separation of VANETs, and the problem is that information dissemination between the relevant vehicles is not always possible anymore. So you can see an example in the picture below. The vehicles on the right are not aware of a possible dangerous situation which is broadcasted by a vehicle on the left. The proposed solution here in this work is, why not adding satellite communication component to the vehicles? The satellite communication link is able to connect different clustered VANETs, and that allows information dissemination also beyond different clusters. You can see an example in the picture below again. Now, also the vehicles on the right are informed about the possible dangerous situation which is detected by a vehicle on the left. According to our methodology, I would like to start with the simulation tool chain. For the simulation tool chain, we started to choose a rural area with a size of 20 to 20 kilometers from OpenStreetMap, namely in the south part of Germany in the region of Baden-Württemberg. Then we converted this data into SUMO road topology network file. SUMO is a well-known traffic simulator, by the way. And we fed SUMO with vehicles we have generated on the edges of the simulation area and also in some of the villages, following an exponential distribution for the timely separation between the vehicles. We also take into account some traffic statistics provided especially for this area. And what we get then is trace files from SUMO, trace files of the vehicles, of their movements. Then in the next steps, okay, we have the trace files now. We load these trace files into NS3. It's a famous network simulator. And we enhanced NS3 by a simplified car-to-car communication module and also by a simplified satellite communication module. And what we then get from NS3 is, of course, the simulation or interesting simulation results. With respect to these results, we focused on a special evaluation metric, namely in-time reception ratio. For that, we defined that a vehicle has received a road hazard warning message in time if the driver is able to stop the vehicle before passing the event location. So basically that means that we check if the vehicle has received the message before entering a critical distance. How we calculate the critical distance, you can see in the formula below. it's important to see the main parts of this critical distance, which is dependent on the human reaction time and the braking distance for the cars, dependent on the deceleration braking value. Here on this picture, you can see an example for a vehicle has received the message in time because it is able to brake before passing the event location. And on the next picture, you see an example. The vehicle has not received the message in time because when it receives the message, it has already entered the critical distance. On the right, you can see a simplified version of the algorithm or the control flow of the algorithm we use to evaluate this in-time reception for vehicles. Okay, on this slide, I would like to show you the main simulation setup. On the left, you can see where we have generated the road hazard event, somewhere in the middle of our scenario. And on the right, you see a table which includes the main important parameters for our simulation setup. For example, vehicle density on that special road, which is 150 vehicles per hour, and that corresponds more or less to the traffic statistics or value of the traffic statistics. We choose a duration of 2 hours for the road hazard warning. The penetration rate for car-to-car, we varied from 0 to 50% with a 2.5% step size. Then we have, of course, an additional penetration rate for car-to-satellite communication that we varied from 0 to 100% with a 20% step size. Here, it's important to understand the meaning of the car-to-satellite penetration rate because it's an accumulative one. So imagine 100 vehicles. If we have a 5% car-to-car penetration rate, 5 out of these 100 vehicles are equipped with car-to-car communication. If we have additionally 20% car-to-satellite penetration rate, that means that 1 out of these 5 car-to-car equipped vehicles is additionally equipped with car-to-satellite. That's the meaning of the car-to-satellite penetration rate. We simulated 30 runs for each data point, and the range for car-to-car simulation, for car-to-car communication, we fixed to 250 meters and 1,000 meters. The coverage of the satellite we assume to be infinity, or basically that means the satellite communication covers the complete or the whole simulation area. For the delay for car-to-car communication, we have chosen 0 seconds, and for the delay for the satellite, we have chosen 1 second. And then we have, of course, varied the rebroadcast interval from 4 seconds to 10 seconds to 25 seconds. Rebroadcast interval is because you have to keep the message alive in our scenario, so each vehicle which is already informed rebroadcasts this information again after this interval. Okay, then let's come to the first results. You can see here the simulation setup for a car-to-car communication range of 250 meters and a rebroadcast rate of 10 seconds. First, a few words according to the graph. On the x-axis, you can see the car-to-car penetration rate in percent from 0 to 50 seconds. And on the y-axis, we can see the in-time reception ratio from 0 to 1. Then you can see different curves in different colors, and they represent the different car-to-satellite penetration rates. So for example, the red one is pure car-to-car, and for example, the blue one is all car-to-car equipped vehicles are also equipped with a satellite communication component. And the core message I would like to show you here is that we can see we have a very significant impact on the performance of our simulation of the car-to-car penetration rate for low car-to-car penetration rates. We have a significant performance increase for the lower parts of car-to-car penetration if we use an additional satellite link. That's very interesting here. But let's have a closer look to that results. And what we can do is what we will do now is we will have a look on two special examples. The first one is, let's consider a pure code-to-core penetration rate of about 8%. Then we can see that we can achieve the same performance with 2.5% code-to-core penetration and 20% code-to-satellite penetration. That basically means that we have an advantage of factor 3 by adding a satellite communication component in that case. Okay, the second example, let's consider this one. We have a code-to-core penetration rate of 28%, pure code-to-core performance. So we can achieve the same performance with 5% code-to-core penetration rate and having 80% code-to-satellite penetration rate. In that case, that means we have more than factor 5 advantage by having an additional satellite communication component, in that case 80% of all code-to-core equipped vehicles. Okay, let's reconsider now these two examples again, but just having a look on a different chart. It's this one. This is a chart provided by Volkswagen, and it shows the progress of the core-to-core penetration over the years by having a look on different introduction strategies. For example, consider the lower introduction strategy here. It's 8% of the vehicles will be equipped with core-to-core communication. That means only upper and upper middle class vehicles. Or this curve here represents the introduction strategy by equipping all middle class and above vehicles with core-to-core communication. Okay. Let's now consider the first example again and have a look on this market introduction strategy for core-to-core. What we can see is, as you remember, with 8% pure core-to-core, we have the same performance as 2.5% core-to-core and 20% core-to-satellite penetration. That means, with respect to this chart, that we can have with pure core-to-core, we can have the same performance we have with pure core-to-core after 16 years, already after 4 years by using an additional satellite link. In that case, 20% additional satellite link for all core-to-core equipped vehicles. And that's an improvement or an advantage in market introduction of about 12 years, here in this example. Then let's consider again the second example. Again, using this chart. Now we are focusing on these market introduction strategies, and you remember we compared the 28% pure core-to-core, which performs the same as 5% core-to-core penetration and 80% additional core-to-satellite penetration. In that case, we have the same performance for pure core-to-core, which we have for pure core-to-core. After 8 years, we can already achieve that performance with 5%, only 5% core-to-core, but 80% core-to-satellite penetration after 1 year. So in that case, we have a performance increase of, or advantage in market introduction of about 7 years, let's say. So what you can see here is adding a satellite component can really speed up the benefit of core-to-core. And that's, in my opinion, very important for the early phase and initial phase of market introduction. Okay, then, to conclude my talk, I started with the introduction of the problem. The problem here we considered was the clustering of VANETs in sparse traffic scenarios. Our proposal then was to add a satellite communication component to connect different clusters, to enable this information exchange also between different clusters. The methodology was to simulate a rural area by using our simulation tool chain of OpenStreetMap, Sumo, and NS3. And then our results we got by the evaluation of the in-time reception ratio. The results have shown that we have significant improvements for low car-to-car penetration rates, and we can see that we have really advantage of several years in market introduction for the car-to-car introduction of the car-to-car technology if we use satellite communication in the early phase of that market introduction. Of course, there's still a lot of work to do in future. For example, simulation with more realistic access mechanisms for both communication technologies. Then we should also consider adapted information dissemination strategies. With adapted, I mean with respect to the special requirements of the different communication technologies. And of course, we should also consider other communication technologies in combination with car-to-car communication, for example, WiMAX or LTE, etc. Okay, that's my talk. Thanks for your attention. If you want to see more results, we have on the paper, so please have a look on that. And if there are any questions, please feel free to ask.
Okay, thanks for that presentation. The floor is open for questions. Yes.
Okay, I have just a question about, so you said it already that you wanted to do it in future work, but did you think about the practical problems of satellite communication, such as the antenna size? So if you see the antenna of a very big tanker in the maritime domain, it are very big antennas that you cannot put on a car, I think. So if you think about KU band, KA band, VHF communication, and then you will always have the problem of the costs for satellite communication. So I know from the maritime domain that band-wise of about 128 kilobits per second, flat rate for a month will cost about $3,500 per month. That's very expensive, and I do not think that the manufacturers would like the customers to invest in such a technology.
You're absolutely right. These are aspects which should be considered in future. We didn't consider them yet or now with within these simulation results. I don't know which satellite receiving antennas you have used in the US, because this work has mainly funded by the Safety Project, and they use a satellite communication using DVB-SH, as far as I know. And we have already equipped our vehicle with this satellite communication component, and the antennas have a size of, it's something like that. So it was not a problem to equip our vehicle with an antenna for satellite communication.
Then I have an additional question. Which provider for satellite communication was it?
It's Eutelsat.
Ah, okay.
And according to the costs, of course, you're right, it's not cheap to launch a satellite and provide services. For that reason, I would also recommend, or I'm interested also in having a look to combine car-to-car communication also with maybe WiMAX technology or LTE mobile communications, which is already there. Okay. But I don't know we didn't have a closer look on the cost factors, I have to admit.
Okay. Further questions? Yeah, oh yes, on the back. And behind you.
Hi. So related with what you just said, like what was the motivation of starting with communication between the cars and the satellites and not using the internet, for example? Like the latencies are similar, even less than 1 second, and we have all mobile phones in our pockets. So I was wondering what was the motivation.
No, the latencies are not similar. For the satellite link, you have very long latency, I would say. Okay. In my opinion, for safety applications, latency of up to 1 second is already very late. For safety applications, which considers the local vicinity, I would say. So for that reason, we want to combine both technologies. So we have core-to-core communication, which is very good in disseminating information in the local vicinity very fast. And then it's to also inform vehicles which are more far away. And for that, if we have slow or a low penetration rate for core-to-core communication, it may happen that you cannot reach the vehicles which are far away. For that, we are thinking about using the satellite communication. And for that, it's not necessary to disseminate this information to the vehicles far away within less than 1 second.
But why not using internet?
I mean, if you consider our example, we have a road hazard warning. Let's go back quickly to that. So we have a road hazard warning here. No. Here in that location. So if you have a vehicle there, then for that vehicle, it's not important to receive the information about that road hazard warning within 1 second. It's sufficient to receive it also in 10 seconds. It's important that the vehicle is already informed if it approaches that road hazard warning. So that's, and for the vehicles in the close vicinity of that road hazard warning, we want to take care, we will use the core-to-core communication technology, which is very fast.
And my question is, how is it different, for example, from the Google Maps hazards that you get when I'm driving my car? I get also this kind of information over the internet. And I mean, I understand the motivation of the vehicle-to-vehicle communication or the DSRC or 5.9 because of the lower latency. But in applications that you don't require this latency, I mean, I expect that the internet communications, LTE, what you were saying, or WiMAX, or even GPRS can be enough.
But what you mentioned with Google Maps is, in my opinion, nothing else than using a different communication technology, not a satellite link, but UMTS, for example, to have access to the internet. So it's basically a different communication technology you use, I think, but you have still think about how to provide this information. And that's not the only possibility for a road hazard warning. It could be any other dangerous scenario. What you also can do is you can detect such a scenario and communicate it to other vehicles.